In this video, I'm going to give you some hints and tips as to how to get started with each of the questions on this paper, the Edexcel paper, Sample Assessment Materials, paper 1. Exactly how you use this video is up to you. You might want to have a go at the whole paper yourself first without any hints and then come back just to the questions you need hints on, or you could play the video and pause it at certain points to have a go at each of the questions after each of the tips. Up to you. All right, let's get started with question 1. The line L passes through those 2 points, find an equation for L. If I've been given coordinates, the first thing I want to do is do a sketch so that I've got it okay in my own mind. Now, a sketch never has to be really accurate, so when I place 3, 1 somewhere, it's not like I've marked off exactly where 3, 1 is, but it just roughly in the right place. 4, -2 is going to be down here. Hopefully that sketch will help you to find all the necessary bits that you need to put together an equation for L. The equation that you write down when it doesn't give you a form for the equation could be in the form y equals mx plus c, or it could be ax plus by equals k. Doesn't matter what form you write it in, as long as it's correct. Next, question 2. We've got a curve with an equation. It's a quadratic, so it's going to look something like, I don't know, yeah. And we're asked to find the gradient of the curve at that point. When I see the word gradient, I also think of the word differentiate. Associate those 2 words in your head as well. After you've differentiated it, I'm sure you'll be able to figure out what to do, which of those numbers to plug into the derivative to find the gradient at that point. Question 3. A vectors question here. Given that A has this position vector and B has this position vector, we're asked for the vector AB, so how to get from A to B, and the length of that vector. I'm thinking a sketch is necessary here as well. We might as well draw it on some axes so we know where the origin is. We've got A is 3 - 7, so down here somewhere. To get to A, and B is over here somewhere, 8 along and 3 up. 8i plus 3j. Note that when I draw these sketches, they're not tiny. In a lesson, if I could cover a sketch with my thumb, then it's definitely too small. Make them big enough to use. We're looking for the vector that goes from A to B, the vector AB. And then it's up to you to remember how to find the length of that vector as well. Question 4. If I can get to it, there we go. Use the factor theorem to show that this is a factor of this. I'm going to leave that up to you to look up again how to use the factor theorem. But if it says to use the factor theorem, then you need to say, by the factor theorem, such and such and such and such. Make it explicit how you've used the factor theorem for the marks. Hence, show that 3 is the only real root of that equation. Well, if I've got a cubic there, and I've shown that x minus 3 is a root, then I know that that other bit is going to be a quadratic. And there's another a word association with the phrase real roots that I have. When I see real roots with a quadratic, I think of the word discriminant. I reckon I'm going to have to use the discriminant in this question. Again, I'll leave that up to you as to how to find that quadratic and then use the discriminant. Question 5. We have a function and we're saying, show that the integral of that function between 1 and 2 root 2 is that. This is a fairly standard integration question. They're just saying, integrate this. It's a show that question so that you can't just plug it into your class whiz. Sometimes if integration pops up in the middle of a question, we can just use the integration button on our class whiz to get a numerical answer. But because it's a show that question and it wants it exactly as a root like that, which our calculator might give, we definitely can't use the class whiz here. Make sure when you're doing integration questions to get the notation exactly right. Don't be sloppy with your notation. So when you've written an integral, write dx on the end. Don't forget to write the limits on it there. After you've integrated it, we use the square brackets and put the limits over there. And then you'll end up doing the expression with 2 root 2 plugged into it, take away the expression with 1 plugged into it. You might need to do some revision about integration as to each of those steps. What I'm saying there is don't be sloppy with your notation, else the examiner might not give you marks for a show that question. You've got to show it clearly. Question 6. Prove from first principles that the derivative of this is this. A very standard question that if you've practiced and revised differentiation from first principles, you should get full marks on, again, if your notation isn't sloppy. The little formula for differentiating from first principles is actually in the formula book. I'm going to write it here anyway. Minus f of x all over h. And this is how I like to lay it out. We write that first, then we write it out with the bits, the necessary bits in it, but without the lim bit at this stage. Simplify that up, and at the stage where you let h tend to 0, be clear what you're doing. So if I've gotten to a bit down here where h needs to tend to 0, I'll write that tends to something as h tends to 0. I'll leave that to you now to fill in those blanks. Question 7. Oh, this paper's full of fairly standard questions here. This is such a standard binomial expansion question. When seeing that, though, there's a warning sign in my head as to a mistake that I could make. That's a really common mistake with binomial questions, with that value in there and factorizing it incorrectly. When that 2 comes out the front, because it was inside the bracket, it's got to have a power of 7 on it. Be really careful with that when you're doing it. And then just be really neat with your layout when you're doing the binomial expansion of that bit. For part B, explain how we'd use your expansion to give estimate of that value. Again, that's fairly standard. You can revise that in your Year 12 textbook as to the method there. Question 8. Just looking at that picture indicates to me what this question is going to be about without even reading it. It's a triangle, we've got some lengths and angles. It's going to be cosine rule, sine rule, or half AB sine C to find the area. If we read it, we've got a lawn, we've got a length. Oh, whenever they give you a picture, they always give you a sentence just that explains the picture. That sentence is redundant. Actually, all of that seems redundant. All of that information is just in the picture. Calculate the area of the lawn. Area equals half AB sine C, where A and B are two lengths and C is the angle between them. I haven't got two lengths on that picture though, I've got two angles. So you're going to have to use either the cosine rule or the sine rule to find another length and then use that. That part B, why is our answer unlikely to be accurate to the nearest square metre? These sort of interpretation questions at the end, worth 1 mark, don't write a paragraph, write a sentence. It's worth 1 mark. Think about how the real life scenario might be slightly different to this pure mathematical picture that we've written down, and refer to the real life scenario. Question 9 gets juicy now. We've got a trig equation with sines and causes in it. And the first thing that springs out to me is this dodgy domain of x. So I've already got that in my head to be careful of that. When I get to the answer, I'm going to have to do a sketch of the graph and find the solutions that are all the way out there. When given an equation with sines and causes in it, or with different trig functions in it, I'm immediately thinking of how to write it with just one trig function in it. And at year 12, the tools, the identities that you have at your disposal are tan x is sine x over cos x, and the Pythagorean one, cos squared plus sine squared is always 1. So you're going to use that to write the equation with just one trig function in it. Then it looks like a quadratic to me. So you're going to have to factorize the quadratic, get your solutions, and at the end, draw a graph to make sure that the solutions that you find are in the necessary range. Question 10. That equation where k is a constant has no real roots. This word association has already come up. We've got quadratic, we've got no real roots. This is 100% a discriminant question. And I don't think I need to do anything more with you there. There's one more thing that jumps out to me before I even do this question. That this one is a less than or equal, a greater than or equal to, and this one is a strict inequality sign. So after you've used the discriminant, check both of those ends and figure out why one of them includes the equals. You could do that by plugging in these two values into the original thing and just seeing what happens. That's after you use the discriminant though. Question 11. Prove that for all positive values of x and y, that thing, and then a counterexample. This is also a fairly standard sort of proof question, and there's actually a page of these sort of inequality questions in the Year 12 textbook in the proof chapter. I think it comes under the algebra and functions chapter or something like that. There's a page of questions that look like this one. A cardinal sin with proof questions is to start with the thing that you're trying to prove. Let me give you a more basic example of that. I'm going to prove that the number 3 equals the number 5. Well, 3 equals 5. That's what we're trying to prove. if I add 1 to both sides of that, I get 4 equals 6. And then I'm going to take away 1 from both sides of that, and I'm going to get 3 equals 5. Fantastic. So 3 equals 5. Nah, that's complete baloney, isn't it? If you start with the thing that you're trying to prove, then obviously it's easier to prove it. So let's get rid of all of that rubbish. When you're doing this question, don't start the line of your logic with this. A tip for this, I think, is to label it rough out the side and maybe play with that a little bit, in which case we might be able to start, we can start with that really. We say, what if this is true? Let's manipulate this. So I'm seeing a square root there. I might want to square both sides. And then blah, 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 blah. Get to something that you can work with. In this case, something that's definitely true. But then when you write out your proof, you want to start with the thing that's definitely true and work from there. It's like you do the rough work to find what is definitely true. You find the thing that we should be starting with it, and then in the actual proof, we start with that, and we work all the way through, this implies this, implies this, implies this, until we get to the thing that we want. There. Yes, good luck with that one. As I said, a nice place to start if you completely, is that page in the Year 12 textbook with a bit more practice. That part B, prove by counterexample that when this is not true, that's well easy, I promise you. Question 10. These spot the mistake questions are increasingly common in these exams. A student was asked to give the exact value to this equation, and we've got the student's attempt. You can read that through line by line and just see if anything springs out to you as to what's incorrect, and something might spring out to you very soon with that one. Hopefully it will. But with these spot the mistake questions, if you can't spot the mistake in a first read through, a nice thing to do is to swap around these two parts. To ignore what that student has done, to find the exact solution yourself to that equation, hopefully not making mistakes yourself, and then compare your answer to the student's answer to find what mistakes they made. In this case, looking at the student's answer and reading that through first will give you a hint as to how to solve this as well. It's one of these ones where it's sort of a quadratic. So at some point, we're like y equals 2 to the x, and you turn it into a quadratic. Yes, swapping those parts around is a nice thing to do if you can't find a mistake in the first read through. Question 13. Start out by factorising that completely. It's a cubic. We don't usually factorise cubics, but it's got an x everywhere, so you just take the x out first. That's x times something, and then you're going to factorise the other bit. Sketch the same curve. So our factorisation will help us to sketch the curve. It'll give us the roots of the equation. Then we've got a new equation that looks a lot messier. But here, play spot the similarities and spot the differences. What are the similarities between these two? Well, that first equation has just been transformed by swapping x for x plus a. So what that's going to do is take the original graph and translate it, which way, if we add a to each of the x's, it's going to translate it to the left I think. So it's going to move the red one onto the green one there. I like this question because it forces you to use the sketch that you've made in part B in order to figure out part C. Think of that cubic moving around, and what value of A could you put in so that that new cubic goes through the coordinate it gives you. Be aware that A could be negative as well. So although I just drew it there moving to the left, hopefully that's left when you see me. That's my left. When it moves to the left, if A was negative, then it would move to the right. So A could be negative as well. But use the sketch that you've done in part B. Question 14. Oh, I'm seeing that. There's just loads of words already, and I can't really be bothered. But it's an exam. And so we get over that. I'm being explicit with that there because that is a common response to see all those words and think this is going to be really hard. So acknowledge that you're doing that, and to just get over it is a really important step. Let's read it slowly and do it. Town's population is modelled by an equation. It's exponential where A and B are constants and T is the number of years. Okay, fair. We've got the line L illustrates a linear relationship between T and log to the base 10p. I'm already thinking what chapter this is. There's a chapter on exponentials in the textbook that does this sort of thing. If we've got an exponential but we plot it on a log scale, then it's going to be a straight line. Over a period of 100 years, the line L meets the vertical axis there, and the gradient of L is 1 over 200. I'll write that on the diagram as I do it. Write down an equation for L. That's going to be fairly easy. Why is that worth 2 marks? Ugh. Log to the base 10 of P is, I'm just going to do this, is mx plus c. There you go, done it for you. Find the value of A and the value of B. This might be slightly harder here. You've got to rearrange this that we just wrote down into this form until it looks like that, and write down what A and B are. Part C, with reference to the model, interpret. That word interpret comes up a lot in maths exams in these modelling questions. Whenever you see the word interpret, you need to refer to the original context. So it's not about talking about the maths, it's about talking, in this case, about the population and time and what happens to the population over time. And then I think part D is about using what you did in part B. And part E, state 2 reasons why this might not be realistic. Similarly to what I said with the previous question, 2 marks means 2 sentences. Don't write paragraphs. Don't waste all that time. Be succinct with your answers. In these ones involving time, one of the not realistic things is often about thinking into the future. So plug a really big value of T into the model and show why that is ridiculous. That's often one of those marks. And the other one will be to do with thinking about population and how population varies. I'm sure you can think of some things right down there. Question 15. The curve C1 shown in the figure has this equation. I'm going to write on the diagram as I do it as this equation. I do this so I don't need to refer back to the words. I can just look at the diagram. The point P, about half along at 2 up, lies on C1. I don't know exactly where that'll be, but we've got a point P on C1 somewhere, let's call it there. And we've got the equation of C2. There we go. the normal to C1 at that point meets C2. So tangent is hugging the curve with the same gradient as the curve. The normal is perpendicular to it. So that's not quite perpendicular, but it's just a sketch. It's just a sketch. We've got perpendicular to C1 there. And we're asked to find Q. Hopefully you can see there how the sketch just puts all of those words into what we need to do. The word normal is another word association. Normal means something to do with gradient, and so I know that during this question I'm going to need to do some differentiation. So think about what we need and we'll work backwards. We need Q, so we need to find the intersection of the normal with C2. So we need the equation of the normal. For the equation of the normal, we need the gradient, and you can get that from differentiating. We've seen what we need, we've worked backwards, we figure out that the first thing we need to do is differentiate. Problem solving tip. Question 16. I think we're near the end here. Now this one looks a bit messy, but again, looking at this, I see a very standard applications of differentiation question. These things always start with a little picture with some algebra in, and then some things that you need to show. Again, in a Year 12 textbook, there's at the end of the differentiation question chapter, it's called either applications with differentiation or modelling with differentiation, one of those two things. But there's lots of these that you can practice. We've got a pool where, again, these two paragraphs are mostly just describing the picture, but the area of the pool is 250 meters squared. Show that the perimeter is this. Something that I'm noticing is that there's a Y here, but there's not a Y in the thing that we need to show. So what you're going to have to do is find the area. We know that that's 250. Use this to plug into the perimeter and write the perimeter without Y in it. The first thing you should do is find the area in terms of X and Y and set it equal to 250. We've got the area of a semicircle there. You can do that. What's the area of a circle? Oh, I learned to rhyme recently for this. Pi r squared sounds like area to me. To find circumference, just use pi d. You remember that one now, won't you? You'll remember that one now, won't you? You remembered it already. Question 17. I'm obviously losing the plot a little bit. I've been doing this for a while now. 17. A circle with that centre passes through that point. Circles questions, as with previous questions, I immediately think that I'm going to be doing a sketch. Do a sketch for all circles questions. We've got a centre at -2, 6, so here somewhere. And it passes to, oh my God, 10, 11, all the way over here. I've done my sketch in the wrong place. I'm going to persevere with it. And then we've got a circle, or a lemon in this case. It goes all the way around there. So that the circle also passes through the point 10 along and 1 up. I think there are a couple of ways of doing that. You could fairly easily, I think, find the equation of that circle by finding the radius of it and write it in the equation of a circle. With the centre there, we've got the centre there, and plug that coordinate into it, I think that's the easiest way of doing it, actually. I was thinking we could do this using some sort of geometry about thinking about the lengths here and symmetry, but that might be hard to write down. So find the equation of the circle, plug in that coordinate, and verify that it's on it. The tangent to the circle at the point 10, 11, so that's down here, meets the y-axis over here at the point P, and the tangent to the circle over here meets it at Q. Oh my God. That's all the way down there. Look how useful this sketch is. Show that distance PQ is 58. These sort of circles questions rely a lot on knowledge of geometry and GCSE circle theorems. So be prepared here to think of some GCSE circle theorems about that. Probably draw the diagram a bit neater than I have. And use your diagram to draw lengths on. Just from there are some lengths that we could already draw on the diagram. One thing that might be useful, something that's often nice to do with these circle geometry questions, is to join things up. Join points in the circumference up to the center like that. You might have to use those radii, and there's something to do with that. I'll leave the rest of the problem solving to you. Draw a neat diagram and think about some GCSE circle theorems. And that's it. That's it. Well done for getting through that, however you use the video. I hope those hints are useful, and persevere with it. So even if after these tips you've had difficulty with the questions, don't just jump straight to the mark scheme to check it. Maybe have a break, go and get a drink, and come back to it, and hopefully your brain will have worked along in the background and you'll figure it out and you'll get the satisfaction from doing so. Good luck with all of that.